Welcome to Summarize Science, where we break down complex research for you. Today, we're looking at a fascinating paper that connects the study of earthquakes to preventing strokes. It's all about using over a century-old physics in a completely new way for medical diagnosis. The paper is titled Zoeppritz Equations, From Seismology to Medical Exploration. Back in 1919, a scientist named Carl Bernhard Zoeppritz developed a set of equations. These equations described how seismic waves, like those from an earthquake, bounce off or pass through different layers of rock inside the Earth. By analyzing these reflections, geologists can map out what's underground, like finding oil and gas reserves. The researchers behind this paper realized that ultrasound waves used in medicine behave just like those seismic waves. Instead of rock layers, the ultrasound waves travel through different layers of tissue in your body. So, they decided to apply the full power of these old equations to modern medical ultrasound. Their main target is a huge health problem, plaque buildup in the arteries, which can lead to strokes. Standard ultrasound is like a simple echo. It sends a wave and listens for what bounces straight back. But the Zoeppritz equations look at how the reflection changes when you send the ultrasound in at different angles. This technique is called amplitude versus angle, or AVA. By analyzing the reflections from various angles, they can learn much more detailed information. For example, they can tell the difference between a change in tissue density and a change in how fast sound travels through it. This is crucial because plaque becomes more dangerous as it hardens, which changes its physical properties in subtle ways. The researchers show something truly remarkable. Using this method, they can measure the thickness of an artery wall or a layer of plaque with incredible precision. In fact, their simulations show it's possible to detect thickness changes that are even smaller than the wavelength of the ultrasound being used. That's like using a regular ruler to measure something smaller than its smallest marking. They also show how the very shape of the reflected wave gets distorted, and this distortion contains information about the layers it bounced off. So, to recap, this research takes equations originally for studying the Earth's core and applies them to medical ultrasound. The key is analyzing reflections at multiple angles, not just straight-on echoes. This allows for a much richer understanding of tissues, like the difference between soft and hard arterial plaque. It could lead to tools that can measure plaque thickness with sub-wavelength accuracy, something very difficult to do today. In the future, this technique could be built into new ultrasound machines. It could even be used to train artificial intelligence systems to spot the early signs of dangerous plaque, potentially preventing countless strokes before they happen. This is a brilliant example of how old science can be repurposed to solve modern problems and save lives.